Okay, this is 2-3, Forms of Quadratics. Our goal today is to identify the forms of quadratics and what they're most useful for. So first we'll talk about standard form. Standard form is a pretty common one. And when we see it in standard form, it usually has like an x squared term, an x squared term, an x term, and a constant term. And we're just going to talk about each of these coefficients in front of the variables, including the c on the end. Those are just standing in place of normal numbers. So we might have like a standard form equation that's like 4x squared plus 3x plus 2 or something like that, where a, b, and c are just the numbers in front of the variables. So each of those numbers actually tells us something. The a value, which is here, the a value, that actually operates the same in each form, which makes it kind of interesting and kind of I don't know, it's very useful to know what a does because it does the same thing in each form. So that'll make more sense when we see other forms. But the a value tells us the concavity and the stretch factor. So the a value tells us whether or not the parabola will be concave up or concave down. Concave up if it's positive and concave down if it's negative. See my little smiley faces there. Concave up if that a value is positive, concave down if it's negative. The stretch factor is just how stretched a parabola will look. So like parabolas can be really kind of sharp and narrow, or like super wide and gradual. Both of those are parabolas, they're just different stretch factors. So a high stretch factor like 6 will be a really sharp pointed parabola, and a low stretch factor that's like a fraction, like a fourth, will give you something more gradual like this. So that a value stays the same in each form. It always tells us the concavity and the stretch factor. The b value, in this form, the b value doesn't do a lot alone. This one doesn't tell us much on its own. You will use the b value in equations, and we'll talk about that in a second, but the b value by itself isn't super informative. And last we have the c value. Let me pick a better color. The c value, this is the y-intercept of the function. So the y-intercept will happen at 0, c. So this one tells us exactly where the parabola crosses the y-axis. So that's kind of cool, super easy to tell. And that, in fact, is actually the most useful thing about the standard form of parabolas, is that it tells us the y-intercept, because it's just like right there on the end. We also need a quadratic to be in this form to use the quadratic formula, which is something we will learn about later, specifically next unit. In this lesson, there are a lot of formulas. And so what I'm going to tell you is that I'm going to highlight the ones that I expect you to understand and be able to use. The rest I'm not going to be picky about. And I'm real serious about that because there are a lot of formulas. There's like a whole section of formulas for each form of quadratics. So what I expect you to use here is the line of symmetry and the vertex and the y-intercept. Let me get a smaller highlighter. These three and the concavity. The other ones we can leave alone for now. So we're looking at something like this. Notice that it has, all of these formulas have A, B, and C as the variables. Those are coming from whatever A, B, and C were in our formula or an equation. So for example, like our, like this example that we did right here, the A value for that is 4. Hang on, I don't want to write it there because I'm afraid you'll, okay, so the A value would be 4, the B value would be 3, and the C value is 2. So we would use those values in our equations. For example, for the line of symmetry, we could put negative B, which is in our case is 3, so negative 3 over 2 times 4, which is our A value. And that would give us the line of symmetry. I don't think that, 2 times 4 makes 8, so that just makes negative 3/8. Not a nice number, but that's fine. That would be where the line of symmetry is. And we will actually practice these formulas with an actual equation in just a second. There you go. Okay. So what our job is on these ones is to identify whether or not it's in standard form. So that's the first thing. If not, convert them, meaning that we need to multiply some stuff out to make it standard form. And then identify A, B, and C. So we don't have a lot of room in some of these. So just know that I apologize for that lack of room. This first one is clearly not in standard form. We don't have an x squared, an x, and a constant term. So we need to distribute on this one to make it into standard form. That gives us an x squared for that first distribution, and then a minus 45x for the second, and then a positive 2x, and then a minus 90. And I'm just going to combine like terms in the middle, which gives us x squared, negative 43x minus 90. And notice that now we have an x squared term, an x term, and a constant term. And so we are also going to identify A, B, and C in this formula, or in this equation. A is going to be the coefficient in front of the x squared term. Please look back at the last page if you need to know where A, B, and C are. But A is going to be 1 in this case because there's sort of this like imagined or implied 1 in front of that x squared. Not imagined, that's a bad word. Implied. So there's only a single x squared, so that's our coefficient for the first one. B is negative 43 because that's the number in front of the x, and then C is negative 90. So we decided that it was not in standard form. We changed it into standard form, and then we identified A, B, and C. This next one is in standard form. Notice that it has an x squared, an x, and a constant term. So that is in standard form, and our job is just to identify A, B, and C. A is 5, B is 2, C is 3. Remember, it's just the number, it's just the coefficient in front of the variables. Except for on the constant term, because it's all by itself. This last one, this is not a last one, sorry, it's early for me. This one is not in standard form. And remember that when we have something that has parentheses squared with an adding or subtracting in it, What that really means is that thing multiplied by itself. So it's not in standard form for sure, and in order to get it there we have to do some distribution again, which gives us an x squared for that first bit, and then a minus x, and then a minus another x, and then a plus 1. And then we still have this plus 1 on the outside. And then we can combine like terms in the middle. I'm running out of room, probably just like you, so I'm going to go up here. X squared minus 2x when we combine like terms. And then these two can also be combined to be plus 2 on the end. So now it's in standard form. And A is 1, B is negative 2, and C is 2. Remember that the sign goes with the coefficient. So because there's a negative right here in front of our 2, that is a negative 2 coefficient. This is in standard form, the next one, and A is 54, B is negative 4, and C is 29. This one, it looks like it has an x squared term, an x term, wait, let's do this, x squared term, an x term, and a constant, but they're not in the right order. So I'm going to say that no, this is not in standard form because it's not in the right order. But all we have to do to get it there is just put the stuff in the right order. And then we can identify A is 2, B is 1, and C is negative 2. Again, those are just the coefficients in front of each variable, and it's nice because it goes in order, A, B, and C. This is now in standard form. The next one is just x squared all by itself. So this is in standard form because there's nothing wrong with it. It's just missing some terms, which is okay. Like really what this is saying is that there's 0 x's and 0 constants on the end of it. And so identifying A, B, and C can feel weird if there's no B and C like terms. But really they're there, they're just 0, like B and C are both 0 in this case, because what we have here is the x squared term. The x squared term has a 1, like an invisible 1 in front of it. This next one, x squared minus 4, you might notice that it's missing like its middle term. And again, it's kind of like this situation where there's nothing, there's a 0 middle term. So it is in standard form, it's just looks weird because it's missing that 0x in the middle. And really we don't have to write that, we just know that there's no x's in the middle. So A is 1, B is 0, careful about that, and C is negative 4. Because the B value always comes from the term with the x, and since there is no term with the x, it's 0. So just be careful about that. It's kind of tempting to say A is 1 and B is negative 4 because that's in order, but this is next in order. So be careful about that. This last one, it isn't really in standard form because we have 2 x squared terms which are making it awkward for us. So we have a 1 in front of the x squared and a minus 2 in front of the other x squared. So we're going to combine like terms here. That's a 1 minus 2 makes negative 1x squared plus 3x. And the term that we're missing on that one is the constant term. There is no number on the end with no variable. So I just added plus 0 to keep myself in order here. So that when I identify A, it's negative 1, B is 3, and C is 0. There you go. This is in standard form. I didn't need to write that negative 1, but I did anyway because it felt easier to see that way. Okay, so let's just practice using some formulas with a function here. This is a quadratic, and it's in standard form, and it's asking us to find the y-intercept, the line of symmetry, and the vertex. So I'm going to split my box into 3 pieces. And then over here I'm going to find the y-intercepts. This is the line of symmetry. I'm going to abbreviate, and this can be our vertex. So the y-intercept, let's start with the easy one. The y-intercept, remember in standard form, the c value on the end of the function is the y-intercept. It's 0, c. And you can see that in our formulas as well, that the y-intercept is 0, c. So in this function, this is our y-intercept. It's just there nicely on the end for us. We don't have to do any math to get it. It's just going to be 0, -4, because it crosses the y-axis at y equals -4. Something else to notice, it doesn't say to find this, but notice that our leading coefficient, our a value, is a positive, which means that it's concave up. So that's just something to notice. It also has a stretch value. This is a stretch value as well, so it's got a stretch of 2, and it's concave up. Let's also find the line of symmetry. I'm just going to go back and show you where I'm getting this formula. The line of symmetry formula is -b/2a. X equals -b/2a. So I'm going to use that formula and just plug in my a, b, and c values. First of all, I should identify my a, b, and c. So a in this function is 2, b is 4, and c is -4. So my formula says -b/2a. My b value is 4, so I'm going to put -4 on the top, and then 2 times 2 on the bottom, because of my a value being 2, which gives me -4/4. That divides nicely, which gives me a -1. So my line of symmetry is x equals -1. Remember that the line of symmetry, and I don't want us to forget the visual here. The line of symmetry is the line where it folds in half. So this function folds in half at x equals -1, which might look something like this. So this is -1 right here, and that's where our function is located. I could also probably have put the x-axis a little higher because it crosses the y-axis. We also know that it crosses the y-axis at -4. So we have a lot of information about this function already. Because of this, we know it crosses at -4, and because of this, we know it folds in half at -1. And the next thing we need to find is the vertex. And this one trips everybody up, and it really doesn't super need to. So I'm first going to show you the formula, because this is what we're going to look at. This is the formula. And I want you to notice something, that this piece, it's in the form of a point, right? It has parentheses and a comma. So this is like the x value, and this is the y value of a point. Notice that my x value is the same formula that we use for the line of symmetry. So there is very little math to do on that part because we already found the line of symmetry. So I'm going to rewrite this function over here, or this formula. The formula says, parentheses, -b/2a, comma, f of -b/2a, and we'll talk about that in a second. But first we already know what -b/2a is because we just barely found that. We just did that, right? So -b/2a is -1. We know that because we just did that. Now we just need to find the y value of our vertex. So let me tell you why that makes sense. We just found the line of symmetry, and we know that the line of symmetry goes through the middle of the whole parabola. And what we're trying to find is this point right now. We're trying to find the vertex. The vertex is always on the line of symmetry, so the x value of the vertex is always the line of symmetry. So if you have this, you already have the x value of the vertex. The only thing you need to do is find the y value of the vertex. And what this means, this right here, this means plug in that value to the function. F of negative b over 2a means plug in this into the function and see what you get out. That's what we always do to figure out what the y value is at a certain x value point. That is something, that's a pretty standard thing in math. When we want to find the y value, we plug in an x. And so if we know the x, we're just going to plug it into the function to figure out what the output is. So I'm plugging in -1 wherever there's an x. And then just computing that. You can do it on a calculator if you want to. I'm going to do it by hand because I don't have a calculator within reach. -1 squared is positive, so that makes 2 plus, there you go, -4 because of that negative. -4, that makes -6, I believe. Yep, I was just double checking on my, yeah. Okay, so it's -6 is the output. Input -1, output -6. Which with our little picture so far, that makes sense. Because this was -4, and that makes sense that this would be -6. It's always a good idea to make sure that your answers make sense. Yeah, that's just a thought. Yeah, so I hope that makes sense. You're plugging in this x value to the function to figure out what the output is, input-output. That's what f of negative b over 2a means. You find the axis of symmetry, or this negative b over 2a, and then you plug it into the function to figure out what the output is at that point. Okay, let's move on to a different form. This is factored form, and we have an a, an r, and an s. Instead of a, b, and c, we already used those. Since a is the same, we keep that. We keep that letter. What I mean by is the same, it tells us the same thing. It tells us the concavity, meaning does it open upward or downward, and the stretch factor. So same exact as the a before, does the same things. Positive a values give you a concave up, negative a values give you a concave down, and then stretch factors, if they're fractions, they squish the function. If they're whole numbers, then they multiply or stretch it a certain amount. And then we have R and S. R is, this is one of the x-intercepts. And it turns out that S is the other x-intercept. Remember that parabolas have two x-intercepts most of the time. And so R and S are those two x-intercepts. If the function doesn't cross the x-axis, then this thing will look different. But most of the time we see things in this form, they will have x-intercepts, and that's how come we have an R and an S. This form, as you might imagine, is really good for seeing the x-intercepts. We really like factored form. In fact, we spend a lot of our lives trying to get things into factored form so that we can see the x-intercepts easy. Yeah. The other thing that I want you to notice here is that there's a negative in the formula. And when we've encountered that before, it means that R and S should be the opposite sign. When we are just looking at R, this says negative R. Our x-intercept is positive R. So this is like the opposite sign of what's actually in the function. Both of them are. So it feels a little bit opposite there, which makes sense. But we switch the signs for the x-intercepts. We'll learn more about why that's the case when we actually graph stuff and actually next unit when we're solving things. But just know that these are both going to look like the opposite sign of what they should be, and we'll do examples of that. On this one, the important, let me find on here. Yeah, the important ones I want you to know, again, is the line of symmetry formula, and the y-intercept and the x-intercept ones. Only those three. Naturally, though, I want you to notice that there's a similar pattern going on here. This is for the line of symmetry, r plus s over 2. This is also the line of symmetry. So remember how we had the x value of a function? This x value of the vertex is always the line of symmetry. Like, those things are the same. So no matter what formula you're using or what form you're dealing with, the line of symmetry and the vertex are going to be related the same way. So we would do the same thing if we find the line of symmetry. We just take that, and that's the x value of the vertex, and then we plug it into the function to find the y value of the vertex. So there are some consistent patterns here that you can get really used to, and it'll be good for you. So we're going to just try this on this function here. It wants us to find 4 things this time: x-intercepts, y-intercept, line of symmetry, and vertex. So I'm just going to split this in 4 pieces, and hopefully I will have room. Actually, I'm more worried about you having room, but we'll try to make it simple. These are the x-intercepts. These are the y-intercepts. Actually, there's only one, so I should not make that plural. This is the line of symmetry, L of s, and the vertex. There we go. The x-intercepts are right here. They're just r and s. This form is made to be able to see the x-intercepts. So r and s, actually let's first identify what a, r, and s are in here. A is 3, that's always the one that's multiplied out front. R, be careful about this because remember it's opposite sign of what you think it is. So even though it looks like a -2 in there, it should be a +2. And likewise, the s looks like a +4 in there, but there's a negative in the formula, which means that we must have plugged in a -4. So now that we have a, r, and s, our x-intercepts are super easy because they're just r and s. The first x-intercept is 2, 0, and the second is -4, 0. The reason that they're in points like that is because because they're points on the graph, but also this is the x value and this is the y value. Whoops. So when you're finding x-intercepts, you put the number here, and when you're finding y-intercepts, you put them here. Yeah, I won't delete that. So that one's super easy because that's what the form is made for. Let's now find the y-intercept, and we're looking at the formula here. The formula says 0, so it's in the point form again. 0, and then for the y, we multiply a times r times s. Seems pretty easy. Let's just multiply our a value times our r value, times our s value. So like just all 3 of the variables we're having are the coefficients. 3 times 2 times -4 makes -24. Maybe double check me on that. 6 times 4. That's right, yeah? Yeah. So we have 0, -24 is the y-intercept. Maybe I should box my answers because we actually had to do work on that one. Great. That's all for the y-intercept. the line of symmetry, the formula is adding together r and s and then dividing by 2. So x equals r plus s over 2. I'm just going to plug in my r and my s, which are 2 and negative 4 divided by 2. 2 minus 4 makes negative 2 over 2, which makes negative 1. So our line of symmetry, again, this time we ended up with the same answer. Our line of symmetry is negative 1 again. Not always the case, of course. It just sort of happened to be that these two have the same line of symmetry. And remember from before, our line of symmetry is the x value of our vertex. So I could look at the formula, but I already know that the x value has to be negative 1 because I found that. And the y value just comes from plugging in negative 1 to our function. So I'm going to replace all of my x's with negative 1 in this function. And then just solve. Negative 1 minus 2 makes negative 3. And negative 1 plus 4 makes positive 3. So we have 3 times 3 times 3, which makes 27, negative 27. So that is our y value. So again, what we did was plug it in. Everywhere there was an x to get the y. Last form that we'll do is vertex form, and then we'll do a little bit more practice and we'll call it good for today. I know it's been a long one, it's longer than usual, but this is important stuff. So, one more form is vertex form. I bet you can probably guess what this form is good for. It's for seeing the vertex, because the vertex is just really plain to see in this one. Much more plain to see. Like normally we're doing sort of a lot of work to get the vertex. This one, it's much less work. So we like it. The a value operates the same as it does with every form. The a value tells us the concavity. Positive for concave up, negative for concave down, and the stretch factor. If it's a fraction, it's squished. If it's a number, it's stretched. If it's not there at all, it's not stretched at all, which is great. Then we have the h value, which notice in the formula it has a negative, so this one ends up being opposite sign, just for future reference. The h value tells us the x value of the vertex. This is also, lost it there. This is also an opposite sign situation. So this, in the vertex, it gives us this number. And as you might imagine, the k value is the other number. The k value tells us, and this is the same sign, which is why this one is a little bit confusing, but this tells us the y value of the vertex, and this is the same sign. So you don't have to switch the sign on this one, and this tells us this value of the vertex. So this one's nice because the vertex is really plain to see, and because the vertex is really easy to see, so is the line of symmetry. So the important ones to know on this one are, I will double check this, the line of symmetry in the vertex, and the concavity and the range. So we haven't included range or domain in any of the ones so far. So we'll talk about, you might see that on your homework, but the idea is, remember from last lesson that the range depends on where the vertex is and the concavity. So if it's concave, if it's concave up, it will be this formula, and if it's concave down, it's this one. And all you need is this k value. That's all you're replacing. So pretty easy. So these are both in vertex form, which is great. So what we want to find in both of these is the vertex, which on this one is nice and easy, the line of symmetry, the stretch, and the concavity. So those 4 things on both of them. And then I want to emphasize here that that the graph that we're going to make here is a sketch. And when I say sketch, I mean like sketch. Like we are not graphing it specifically because we don't really know how to do that yet. We're just sort of getting an idea, just sort of like we did on that first problem today, of where the function is. And actually we'll have a really good idea of where the function is and a lot of information just because of the vertex, the line of symmetry, the stretch, and the concavity. So we will have a lot of information. So really quickly, let's identify A, H, and K. In this function, A is negative. It's important. H, remember this is the opposite sign one. This one is the one where you switch the sign. We wrote that down on the other page. This one's positive 1, and this one, same sign, negative 3. So A is negative 2, H is 1, K is negative 3. So the vertex is just H comma K. That's what our formula says, just H comma K. So our H is 1, our K is negative 3, and that's it. Remember that this is the same sign. Nope, that's opposite sign, sorry. Opposite sign. And we need a different color here. Same sign. And by opposite and same sign, I mean from the formula or the function here. This looks like a negative 1. We put in a positive 1. This looks like a negative 3. We put in a negative 3. So that's what I'm talking about with opposite and same sign. The line of symmetry is super easy as well. The line of symmetry is just x equals h. So the line of symmetry will just be x equals 1 because of that h being 1. The stretch factor comes from the a value. The stretch is negative 2. So the stretch is 2. It's going to be stretched by 2. And the negative tells us the concavity, which is concave down because it's a negative. I'll do like my sad face here. It's a negative a value, which makes it concave down. So here's our information. We have the vertex is at positive 1, negative 3. So I'm going to put my vertex there. And then it's the line of symmetry is just along that line. We already know that because we know it goes through the vertex. And then we also know it's concave down and that it's a little bit stretched. So I'm going to just draw a kind of stretched parabola opening downwards because it's concave down. And again, it's a sketch. We're not trying to make this exactly the graph. We're just trying to see in general what it looks like. It's helpful for us to like do this activity to figure out what in general it looks like. This next one, the a value is 5, comes from there. The h value is, so there's a positive 3 there, but the h value is the opposite sign, so it should be negative 3. The k value is the normal sign, same sign. Whoops, I wrote 24, it should be 29. So our vertex, h comma k, is negative 3. That's the h value. K is 29. That's my vertex. Remember, opposite sign, same sign. The line of symmetry is x equals h, which is negative 3. And I want you to know also that the notes that are probably attached below this video have a lot of mistakes in there. There's there's one on the first example we did. I got the line of symmetry as, first of all, I wrote line of symmetry as y equals. It should be x equals. I must have been tired when I did these notes before. But it also should have been a negative 1 on that first example. The notes I just took are correct, but the ones below are not. Same thing sort of on these two. I wrote the line of symmetry as a y equals. It should have been x equals. Math teachers get stuff wrong too. So our stretch factor is just the a, so our stretch is x. I don't know why it does that lately. It's just 5. The concavity is, because a is a positive value, the concavity is going to be concave up. There's a little smiley face, positive eyes. So right now we have that the vertex is at negative 3, back 1, 2, 3. I also graphed this. Oh no, I graphed it right on my paper. Negative 3 and up 29. And honestly, I'm not going to count these lines. I just know that it's 29, and I will write the vertex just so yeah, there you go. And I also know it's concave up, and it's super duper stretched. So I'm going to draw this as like a very sharp parabola. It's very skinny when it's stretched, and that's my sketch of the graph. So that's that for this lesson. Next time we'll talk about graphing them better than this. This is just a sketch, but this is a really good exercise to do in order to just know whether your answer looks right or wrong when you're actually graphing them. So it's good for us. Let me know if you have any questions. I just want to remind you guys that we have a Zoom every Friday at 11, that you're welcome to hop on if you're having problems with the homework, or really if you just want to do your homework with company. I just hang out on a Zoom meeting from like 11 to 12.